Hi, and welcome to my lesson that is going to be under the category of forces and Newton's laws. And specifically, we're going to go over an example of an Atwood machine. So an Atwood machine is effectively kind of like an elevator where you have a counterweight. But in this case, we're looking at a scenario where there is no motor, it's just a freely spinning pulley. So I have two masses here. I'm going to label them as M1 and M2, and so we are going to allow this system to get set into motion. And I'm making these one larger than two, so that way it clearly is going to accelerate in this direction. So if you look at the string, it is clearly going to accelerate into this direction, and that is a very key observation to make. And so what we are going to do is to simplify this, and there is other ways to do it, but to simplify it, we're going to make this direction a positive direction, meaning the direction of the string's acceleration, that is going to be a positive direction. So with that in mind, let's go ahead and make free body diagrams for each object. So what you want to do when solving any sort of force problem, make a free body diagram for each individual object. Then we're going to use Newton's second law to make at least one equation for each of those objects. You'll want to make an equation for Newton's second law for each object in each relevant direction. Now the horizontal direction here is not relevant. There's no forces in the x direction, so we're just going to neglect that. So that means that we are going to have two free body diagrams and two equations. So the sum of all forces acting on object number one is equal to m1 a1. So it's the mass of object one times the acceleration of object one, and that is something I can state no matter what, regardless of the free body diagram. Okay, so let's go ahead and make our free body diagrams. And in fact, tell you what, I think I'm going to take this and move that up here for now so I can give myself some space to work on my free body diagrams. So if I were to make a free body diagram for object number one, so I'm just going to go ahead and draw an arbitrary box. This is going to represent M1. So my free body diagram should look something like this, where I have a force acting down due to gravity, so that is going to be M1G acting down. And then there will also be a force acting up, and I will call that force the force of tension. And I should draw this force smaller than M1G because clearly it is going to be accelerating down. And so that's really all I need for object one. And then for object two, right, so this is mass 2, now I want to draw a free body diagram for that. So in this case, we have a force of tension. Okay, so I'm going to draw that force of tension to be basically about the same size as this one. Maybe I can make that slightly longer, just that way they look a little bit more symmetrical. And then I'm going to also have a force of gravity acting down. However, in this case, it is going to be M2G. And notice that I've tried to make this at least a little bit smaller than the force of tension, which should make sense because this object is going to be accelerating upwards, right? This one is going to accelerate up, and so this force of tension should be larger than the force of gravity acting down. So here's my two free body diagrams, one for each object, and now I'm going to go ahead and start making my equations, at least one for each object. And so I've kind of already started the one out, so the sum of all forces acting on object number one is equal to MA for that object. So that's M1 A1. This in turn is equal to the things that I've recognized from my free body diagram. So as I said, this direction of acceleration is going to be positive direction. So that means that this here is a positive force and this here is a negative force. But for this object, up is going to be a positive direction, right? For this one, down is a positive direction. So for this one, this is a positive direction and this is a negative direction. So let's keep that in mind. So with my free body diagram for object number one, I'm going to go ahead and express M1G. So I have M1G minus the force of tension. And that's really all I need. Now I'm going to go ahead and work on my sum of all forces for object number 2, which is equal to M2A2, right? That's the MA of object number 2. So let's look at our free body diagram. In a positive direction, we have the force of tension. So I'm going to write that first just because it's neater that way. Minus M2G. All right, and that's really it. I'm done, except for maybe one realization. You might realize that the acceleration of object 1 and object 2 is the same acceleration. So having any sort of subscript is unnecessary, and I'm going to remove it. They are the same acceleration. So why would I bother having an acceleration for object 1 and acceleration for object 2? The same is true of the force of tension. I'm not going to bother having a force of tension for object 1 and object 2 because they are the same force of tension. So in fact, these two forces of tension are an action-reaction pair. If I were to cut the string, I'm getting rid of the force of tension on this object. I'm also getting rid of the force of tension on this object. We always assume that the string is massless and is not an elastic string. So that would allow both objects to accelerate at the same rate. Okay, so now that I've made that realization, I have two unknowns here. I have an acceleration that is unknown and a force of tension that is unknown. This part of my equation here, where I have the sum of all forces, is no longer needed. In both cases, that was just there to kind of get me set up. No longer needed, and I can kind of just ignore it. Okay, now I'm just focused on this part of the equation. Typically what happens here is we want to solve for the acceleration of the system, or we would want to solve for the force of tension, either one, but let's work on the acceleration. Once you get one, you can go back and just plug in for the other one. So let's say that we're able to determine the acceleration of the system. Clearly, once I have that, I can then figure out, plug it into this equation and find the force of tension. But I don't have either one of these two. So I have two unknowns in this equation, therefore I need two equations. So now that I have the two equations, I can solve. Here's what I'm going to do. For both of these equations, since the force of tension is the same, I'm going to solve each equation for the force of tension. I'm then going to set the two equations equal to each other, and I'm then going to solve for the acceleration. So here we go. Let's solve both equations for the force of tension. So I'm going to add each side by the force of tension, and I'm going to subtract each side by m1a. So that means that the force of tension is equal to m1g minus m1a. Okay, so that's for the top one. Added each side by force of tension, subtract each side by m1a. Let's do the same thing for this equation down here. Let's get the force of tension all by itself. To do that will be simple. I will just add each side by m2g. So that means that the force of tension is equal to m2a plus m2g. Now that I have both equations set to the force of tension, I will set basically this part here, I can now say is equal to this part here. So I will just simply set them equal to each other and solve for a. So let's start with this. I'm going to rewrite it. m1g minus m1a. And in fact, I can see I'm going to have a problem if I don't move this over a little bit. So let me go ahead and do that. That'll be better. So that will be equal to all this stuff. So that's m2a plus m2g. All right. So this is equal to that. Let's get all of the a's on one side and the g's on the other, and then I can go ahead and do some factoring. So I'm going to add each side by m1a and subtract each side by m2g. So m1g minus m2g, so that's going to bring this part over to the left, and I'm going to add each side by this to bring it over to the right. So M2A plus M1A. And now that I've got all the A's on one side and the G's on the other, I can go ahead and start doing some factoring. I don't really have to factor this part out, but I could. Sure, why not? So that means that G times M1 minus M2 equals A times, and I'm going to go ahead and put it in the same order, M1 plus M2. All right, I just flipped the order of the M1 and M2, but that's fine. And so now I just divide each side by M1 plus M2, right? Divide each side by M1 plus M2, and that will cancel. And divide this side by M1 plus M2. And now, in fact, I'm just going to go ahead and erase that little part there so it's a little bit neater. There. And so now you can see that I have an equation for the acceleration. Okay. If I have numbers, I can go ahead and plug them in at this point and solve for the acceleration. If I don't have numbers, I could take this whole equation and plug this in. God, that would be a mess. But I could take this whole equation and I could plug this in right there. Just substitute it in. And then I'd have to distribute it, and it would be a bit of an algebra mess, which is why we're not going to do it. But you could. There are scenarios where it can be a bit sloppy, but you would take an equation that looks fairly complex and put it into another equation and do a substitution. That could be done. But on the AP test, you very well could get a question that says, here is this scenario. Determine the acceleration of the system in terms of M1, M2, and G, right? And so determine the acceleration in these terms. This would be your final answer, okay? And that would be your answer. No numbers, that is your answer. Please get used to manipulating the variables. It is a necessary skill. It is not even just for testing purposes. Just think of it this way. What if you were an engineer trying to test a system? What if you even wanted to find the friction inside of a pulley system and you're going to test it time and time again? We would take this equation and effectively just kind of like add in friction basically, which we're not going to do right now, but I'm sure you can understand the idea behind it. And so you would run this experiment time and time again. And you would probably have an Excel spreadsheet and you would plug in your numbers. You would just basically put this equation into your Excel spreadsheet, run the numbers, find the acceleration of the system each and every time. So that would be it. So this actually can be a very useful skill. It is necessary to understand the skill to be able to manipulate the variables and get to this point. So here's the breakdown. Take your system and draw a free body diagram for each individual object. Okay, draw the forces acting on it. Then make an equation for Newton's second law for each object. At least one equation for each object in each dimension. In this case, we did not have a need to draw the horizontal direction because there's no forces in the horizontal direction. And then recognize what variables the two equations have in common and recognize what can be substituted into the other. So effectively what we did, the way I structure is set both equations equal to the same variable and then set them equal to each other. Otherwise, you can take this equation, set it equal to the force of tension, and take this equation and plug it into that one. It's the same thing. It's the same thing. Either case, go through, and then you have to factor out one of the variables and solve for it. So that is an Atwood machine, which is the same thing as an elevator that has, the motor's been burned out and all of a sudden it starts to fall. Hopefully that doesn't happen, but there would be a counterweight there to at least slow your descent in some way. And that's the problem. If you have any questions, please reach out to me and let me know, but I hope that was clear, and I hope that you can see where this is going for other problems. Just to give you a little peek into how it might address to other problems. What if you have an inclined plane with a pulley at the top? So here is a box. Let's just say it's the same boxes of M1 and M2. So this is the heavy box with a pulley, right? And I hope that you can see that this is virtually the same thing, just with the inclined plane added in. Make a free body diagram for each object. you'll have to notice that you'll need two equations for this object, because you need one for the x direction, one for the y direction, and I would treat that to be my positive direction since it can actually go upwards. If this one's heavy enough, it's going to go upwards even if there is friction here. I can go over that another time, but I just want you to at least preview that a little bit. So with that, have a good one. Take care.